All right, everybody, welcome back. We are now going to go ahead and start Chapter 7. So again, we're using Strogatz, so we're in Chapter 7 of Strogatz. And what we are doing in this chapter, we're acknowledging the fact that we have gone up from one-dimensional systems to two-dimensional systems. And while we showed for autonomous systems it was impossible for there to be periodic behavior on a line specifically, that is not the case in two dimensions. When we move up into higher dimensions, we have seen there is now periodic behavior. We are allowed to oscillate, and we've seen that there are some new behaviors, some new long-term behaviors that we have to now consider. And it was simply due to the fact that we have changed the topology of the phase space that we're working in. So let's see about at least introducing the idea of maybe what the difference is between the periodic behavior we've already seen with nonlinear centers, and what makes it different compared to something called a limit cycle. And in order to stress that, we're going to go ahead and take a look at the following two systems. And feel free to plot along in p-plane to see what exactly these systems produce. And in plot A, we can see that there is certainly a, I didn't mark it on here, but I can certainly draw it. It would appear that there is a, yeah, that would be right about there. It would appear that there is a, oh, it should actually be right at 1, shouldn't it? Yeah, there we go, right at -1. Yeah. It would appear that there's actually a saddle at that location. At x equals -1, y equals 0. There's a saddle, and there is a nonlinear center at 1, 0 in this system A. And that's all fine and good. We saw how to deal with these kinds of systems, or to verify that we have this particular kind of periodic behavior in 6.5, talking about conservative systems. So sure, and actually you can go ahead and see that there are a whole bunch of these closed loops, right? This is a center. There's a whole bunch of closed loop trajectories surrounding that nonlinear center. And in fact, you can show even further. And actually, let me do that in a different color so it stands out a little bit better. Yeah, do we want to do it in black? Let's do it in blue. You can see that there is, well, let's see, there he is. Okay, qualitative, right? This is a very qualitative sketch, right? You can see that there are two, the separatrices from this saddle point section off. They kind of contain that nonlinear center and periodic orbits that surround it, and separate it from these unbounded behaviors that we see outside. And if I put another collection of green here, there's another unbounded solution off to the left. So there really are three different solution domains, or three different collections of initial conditions that produce various behaviors. Two of these regions are unbounded, and they push off to -infinity in y and in x. But if we happen to be inside that little loop, then we have a whole family of periodic solutions. Compare that against this system B on the right. Right, if I were to kind of play with the initial conditions a bit, right, I can change up where I want to start. And I can see a whole bunch of spiraling behavior going on inside and outside this loop. And I can continue that out here, sure. That was a terrible last trajectory. There we go. We see a whole bunch of spiraling behavior, but there is but the one periodic solution, right? So this is what's known as an isolated cycle, or an isolated trajectory. Much like our fixed points are isolated from one another, right? We can separate them from each other. So there's a, if we zoom in close enough on any fixed point that we've studied, it is the only fixed point in the area. as opposed to non-isolated, which is what's going on in picture A here, with these periodic, this whole family of periodic solutions. These periodic solutions are not isolated in A, but there is one solution, one periodic solution in B that is isolated. And this guy, if I ask that question, what makes these guys different? They are different for a number of reasons. First, they have a different number of fixed points. Sure, no problem. Right, we can see that. So if these systems are going to be conjugate, they need to have the same topological features. So they need to have the same critical points in their vector fields, or the same zeros, I should say, which means, okay, we have a different number of fixed points, the types are different, right? Two, we're talking about this cluster of closed orbits, the family of closed orbits in A, as opposed to an isolated closed orbit in the B system. Furthermore, system A has unbounded limits, or it has solutions with unbounded limits. But all of these solutions in B, if I come back up, all of these guys have to approach this circle. They have to approach it. It's interesting that that's the case. And when we do that, we get something called a limit cycle, right? When we have this isolated closed orbit, we call it a limit cycle, right? And these limit cycles can have various stabilities. I'm saying that this one in B is a global attractor, right? Everywhere except the origin gets sucked into that limit cycle. And if I'm on the origin, I stay at the origin as a fixed point. But yeah, it turns out that we can also have unstable limit cycles, right? Or repelling limit cycles. And some combination thereof, very much like we have stable, unstable, and semi-stable for one-dimensional systems, or one-dimensional fixed points of one-dimensional systems. We get the same sort of dichotomy between stable and unstable limit cycles. And we could have these weird degenerate cases in between for inner or outer semi-stable, right? And we can see that these are not just limited to circles either. Right? They're not just limited to these perfect round objects. If I talk about one of the more prominent, or we'll say featured, dynamical systems of the early 20th century, something that spurred a lot of work toward understanding these kinds of systems, we go to the van der Pol oscillator. And this guy is derived from an electrical circuit. And frankly, I really don't know too much about it, and honestly don't care too much about what the actual electrical circuit does. But I do note that there are a few features to pay attention to. In particular, this dynamical system behaves much like a damped oscillator, a damped like mass spring system, or a damped electrical circuit, excuse me. So we have an RLC circuit where the resistance is just going crazy. It changes based on what the current, or based on what the present value of the charge is on the capacitor, right? So we can go ahead and map this out. We can plot a numerical representation of the vector field and try to see what our numerical approximations look like for these orbits. And as it turns out, we see a limit cycle again, right? And this, again, I've highlighted this guy in red on the phase portrait. He is, again, globally attracting away from the origin. The origin is an unstable spiral, so just like the previous example, we're actually we're oscillating in the other direction. First example was in the counterclockwise direction, and now we have something in the clockwise direction, so orientation does matter as we move forward here. But the idea is that this damping term is trying to make sure that we lose energy, we dissipate enough energy if the current is too high, or if the charge in the system is on the capacitor plate is too high. And if it's too low, it's going to try to add charge. It's going to try to store charge on that capacitor plate. And it's this balance between trying to bound high energy states and trying to amplify low energy states that produces this sort of limit cycle, that produces this periodic behavior where we are not blowing up to infinity and we're not shrinking down to a point either. So this is one of the routes, shall we say, to a limit cycle, that you can just produce this guy by making sure you have an instability or stability at the origin, and you reverse that stability when you're far enough away from the fixed point. So it pushes, so in this particular example, we are pushing solutions away from the origin, but keeping them bounded. And the red limit cycle is what's produced in the limiting set, or the limiting behavior. The takeaway from this is that there's more than just an asymptotic stability to consider in higher dimensional systems, right? We don't just have to go toward fixed points in the limits, right? We can have these limiting periodic behaviors as well. And to understand how, or what I mean by asymptotic stability, and what other kind of stability that we'd like to say here, because this red limit cycle is not asymptotically stable, it's a different kind of stable, right? We're noticing that solutions want to go toward this cycle, but they're not staying at a fixed point, right? They're moving along with the cycle. So we'd like to call that a stable trajectory, but we don't quite have the terminology for it yet. So this is what we're going to develop right now. So we're going to make a definition. We're going to say that for this system, x dot equals f of x, a non-empty set S sitting in the phase space omega is called invariant if any solution x of t with an initial condition that begins, or with an initial condition in this set, remains, and the solution will stay in the set for all t, and technically I should go ahead and say for all t, erase. For all t greater than or equal to 0, right? So that's forward invariant, there's backward invariant. So in this case, I think that's what I was doing with the original definition. It's just to say that this is true for all time, forward and backward. So if there is a dichotomy, you can say forward invariant, and that'll be the talking about the omega limit set. We'll talk about alpha and omega sets very shortly. But invariant typically means in both time directions, unless you specify forward, which to some people is the default, or backward, which is essentially the default for no one. But anyway, make sure that we understand the direction that time is moving. Right? Usually forward is what we're gonna take here. So forward time. But anyway, examples of invariant sets. Fixed points. Fixed points are invariant sets, right? If I start on a fixed point, then I stay on there for all time, forward and backward. So fixed points are invariant sets. Stable and unstable manifolds are also invariant sets. These are all the initial conditions that either flow toward or flow away from a given fixed point. So if you are going to start on a stable manifold, you are sure going to stay on that manifold, right? Nothing's going to make you deviate away from that, away from your target, which is the fixed point that you're flowing toward. You could also have closed orbits as invariant sets, right? So this guy, this red limit cycle here, if I start on the limit cycle, I close up after a certain amount of time, which means eventually I have to come back to where I started. And since this is a deterministic system, that means I repeat. So it means once I get inside that red set, once I'm on that curve, I stay on that curve. So in particular, limit cycles are closed orbits as well. So limit cycles are invariant sets as well, right? So not just limit cycles, but coming up to the original example, all of this family of closed orbit solutions in part A, right? They're all periodic solutions. So these guys are going to be invariant sets as well. Now, why do I care about invariant sets? Because I can go ahead and tell you about their stabilities. And I'm taking these definitions from some older texts. Perko is one of the texts that I'm using. And let's see, I think this particular definition comes from Kuznetsov. And I'll go ahead and cite these guys eventually for you. But these are the texts that I'm pulling these definitions from. And for stability's sake, we're going to go ahead and say that an invariant set is stable if for any sufficiently small neighborhood U containing that set, there exists a neighborhood V containing S such that if the initial condition is in V, then the flow stays in U for all time greater than 0. So again, this is one of those forward notions as opposed to by infinite, so forward and backward. But this definition is due to Lyapunov, so we call it Lyapunov stability. And this is a little bit trickier to understand. I'll give you a picture of that in a moment, but finishing the definition, we also have asymptotic stability, where this invariant set is stable, asymptotically stable, if there exists a neighborhood U containing S such that once you're in U, your limit goes, or your initial condition will flow to S in forward time. Okay, so just to put that in perspective, coming back to, let's see, maybe we'll do this. Yeah, so coming up here to this semi-stable set. Lyapunov stable, let me do this in this color, there we go. Lyapunov stable says that there is a set that contains the limit cycle, and actually I probably want to do that where you can still see the limit cycle. So here's my highlighter pen. So maybe this guy would be U, or you know what, this drawing feels familiar, like I'm doing this again. Ah, yes, indeed. Okay, so I don't have to go back to this example. So let me go ahead and kill that off. There we go. Let's go down the page a little bit. So back to the definition. We have Lyapunov stable versus asymptotically stable. And we say that an invariant set is unstable if we replace these time notions with their corresponding negative and minus infinity. We'll call them cousins, I'll say. Right, so we're going to go ahead and make sure that unstable is just stable in backwards time. So an example of stable fixed points, right? So stable fixed points are stable. Unstable fixed points are unstable. Really? Yes. So the idea, though, for a saddle, though, saddles are neither stable nor unstable based on these definitions. And specifically, I'm thinking asymptotically stable, right? So any neighborhood, right, this U set that we're talking about in definition 2, any neighborhood that I outfit around a saddle point it's going to contain both stable and unstable orbits, or it's going to contain parts of the stable and unstable manifolds. So eventually in forward time, I'm going to have to leave U along the unstable manifold. And in backwards time, I would have to leave U along the stable manifold. So solutions will eventually have to leave whatever set I try to put around whatever open set I try to put around so I suppose you can all see that. Anyway, let's see, whatever open set that I want to put around the saddle, solutions won't stay there. So that means that this fixed point, this saddle point, can't be stable and it can't be unstable. So it's kind of strange in that sense. It's weird, right? It's not stable, it's not unstable, it's something else. So stability is not this perfect dichotomy that we thought it was. Now, as for Lyapunov stable, this is why it looked familiar, right? This is why my drawing looked familiar to me. It's because I've already done it. So the yellow highlighted region, let's say that was the U set, right? In this definition, we have a U set and we have a V set. So for any sufficiently small neighborhood U containing S, right, this yellow highlight, there is a neighborhood V containing S such that where all my initial conditions are coming from, there's a V set that is going to have to contain U here, or maybe a V set that is containing S at the very least. And my initial conditions will eventually throw me inside of the U, right? So eventually I'm going to enter the yellow region and then stay there, right? So that's the idea. There is no limiting fixed point, but instead the orbits are attracted to the limit cycle. Moreover, once we enter U, they eventually approach the cycle, right? So in some sense, this is kind of a blend of both Lyapunov and asymptotic stability, right? If you are asymptotically stable, you are certainly Lyapunov stable, right? But Lyapunov stable is a bit looser. It's trying to make sure that we're not restricting ourselves just to these fixed point solutions in two-dimensional systems. And the thing that makes it different, asymptotic stability is more of a local phenomenon, and Lyapunov stable is accounting for more of a global phenomenon. So far what we've been talking about are all of our work, all of our techniques have been for local phenomena, except for what we did in 6.5 and 6.7. But up until then, everything we did was local. And now that we have this idea that a periodic orbit here is not a point, we can't zoom in around that cycle with a disk-like open set, right? The analysis now has to extend to to a broader collection of sets. So this is something where we can't just apply. We can't just go straight to a local. We can't zoom in around a single location, because that limit cycle exists in a lot of different places. Hence, global versus local stability. Now, just as much as we want to figure out when limit cycles exist in our systems, it would also behoove us to know when they don't exist. So there are three primary tools that we use to confirm that these limit cycles don't exist, and that would be the focus of 7.2. We'll talk about the three different ways that we can detect or to rule out limit cycles. And we do that via showing that the system is gradient, or showing that there is a dissipating function, something called a Lyapunov function, or if the system is lucky enough to have a Dulac function, right? We'll satisfy Dulac's criterion, which is effectively a divergence test. And we'll see exactly what I mean in the next couple videos. But until then, happy studying.